So it's now recording. So perhaps I will just start with a brief introduction. In the meanwhile, I hope that other people will come in. I would like, first of all, to apologize. Okay, let me, sorry. I'm meeting more people. Okay. So I was saying that, first of all, I would like to apologize for the failure with the meeting the day that was supposed to occur. And as every participant, Fredrik and I were struggling to enter the Zoom link without any success. And then at a certain point, we just gave up because it was impossible. So my apologies for that. And this is our third webinar of this 22-23 series. And it's my pleasure to have here today Fredrik Falkenström. I hope that I'm not very far away from the correct accent. But Fredrik is professor at Linköping University in Sweden and is also currently associate editor of psychotherapy research. His focus has been on using cross-like models with structural equations and HLM to study processes in psychotherapy, often using process outcome designs. He has been interested in common factors in psychotherapy with a particular emphasis to therapeutic alliance and on how the study of these factors may improve psychotherapy efficacy. One interesting and innovative feature of his work is how to infer causality in non-experimental designs using precisely cross-like models. So thank you very much, Fredrik, for accepting to take part on this webinar series. It's a pleasure to have you here. So the floor is yours. And I will admit some more people now. And I think we should begin if you want.
Thank you,
everybody, for being here.
And thank you for inviting me for this. Mm-hmm. I will start because I have quite a few slides, and it's always difficult to know how much to include in this. It's like I think it's like 40 minutes we said talking, and then some 45 minutes, and then some questions and the discussion. Yeah. I usually think it's good if you have like, there are things that I'm saying that doesn't make sense, or there are like things that you need me to explain a little bit better, that you just interrupt me when I'm speaking and ask those kinds of questions. While if you have more like bigger questions, more like discussion-like questions, then we can keep those until the end. That usually makes most sense to me. So I will start by sharing my screen, and if someone can just say if it looks right.
Perfect.
Perfect, thank you. And so this webinar is, as Miguel said, is about using cross-lag panel models for mechanisms of change research. And I say it's an introduction because we won't be able to cover everything related to this subject in such a short time. I hope to be able to get you a little bit interested in this, why we would do this, and also give you a sense of what it is. And then there is the possibility of some further reading, because I will provide some references towards the end that you can continue with. So first, I'd like to say a few words about what is a mechanism of change, obviously, because that's what the primary reason that I'm interested in using these kinds of models. So a mechanism is usually defined as something that explains the effect of an intervention on outcome. So it's kind of an intermediate variable, something in between the intervention that we do and the outcome that we want. So in psychotherapy, this could be some kind of change in the brain, in the neural systems, or physiological thing. It could be cognitions, thought patterns. It could be emotions that we want to either regulate upwards or downwards, or whatever, depending on how we understand the problem the patient comes with. or it could be some kind of behavioral change, but it's something that we're targeting with our interventions in order for the patient to become free of their symptoms or problems that they seek therapy for. It doesn't necessarily have to be the same as what we think is the mechanism of onset, the cause of the disease, so to speak, or even it doesn't necessarily even has to do with what we believe is the maintaining factors, but usually these are the same things. There are some exceptions to that. For instance, we might be able to make someone less depressed, even if their depression is caused by genetic factors in combination with some early life stressors. We might be able to make them less distressed by focusing on current interpersonal support, stuff like that. So interpersonal psychotherapy is usually, they usually talk about, we don't care that much about the onset, we care about their current interpersonal relationships and what kinds of support they get from those. We don't know that much about mechanisms from empirical research, that is. I mean, we have all these very elaborate theories of mechanisms. All our psychotherapy theories have their own specifications of what the mechanisms of change are. But because we don't have that strong empirical evidence for it, it's an important task for us to study this. And a very influential paper from 2009, I think, or 7 maybe, by Alan Kastin. He came and said that we have no evidence actually for any mechanism for any psychotherapy theory. And I don't think, if we use those criteria that he has, I don't think it's that much more nowadays. But by studying mechanisms, we can find what drives change in therapy, so to speak. And by finding that, we would be able to refine treatments. We could simplify by removing some things that we thought was important, but may not be as important empirically that we thought. Or we can put more emphasis on those mechanisms that we find really are related to outcome. And there are examples from other fields of science that identifying mechanisms has been important contributions to scientific progress. And I put in this picture here of Franz Mesmer, who you probably are familiar with the guy who used hypnosis to treat patients, and he had this theory of animal magnetism as the mechanism of change for his treatment. And actually, I had this talk with Alan Kastin not too long ago, and he mentioned an interesting example related to Mesmer. Apparently, there was this commission that was set up at the time. That was like long ago. It was like the Times equivalent to like NICE guidelines or something like that. They were testing whether this theory held up, and Benjamin Franklin was part of this commission, and they actually didn't doubt that the treatment, Mesmer's treatment, worked. That was not the focus of this. They were convinced that it worked, but they didn't believe in the mechanism, this animal magnetism, and for that reason only, they said that this treatment was unscientific. So that kind of speaks a bit to the importance of mechanisms, that even if something is clearly working, if we don't find, if the mechanism is not supported, then it's still seen as unscientific. There are other examples, but I won't go into them now because it's not much time. The method that is most often used for studying mechanisms is mediation analysis. So mediator and mechanism are often used more or less interchangeably, but they are conceptually different. The mechanism is the phenomenon itself, so to speak, that which we want to draw inferences about, we want to know about, and the mechanism is the mediator is the method we use to study that. So in that sense, all mechanisms are mediators, but not all mediators are mechanisms, as this quote from Kramer et al. Says. And this little diagram in the bottom here is the classic diagram for mediation analysis. We have can you see my arrow, by the way? This one? Yeah, good, because I will use that to point. We have the independent variable, the treatment or the technique, which has an effect on outcome, but we also believe that it has an indirect effect on outcome via the mediator variable, which is the something we measure that we believe is related to the mechanism. So mediation analysis usually consists in getting some kind of estimate of this indirect effect of treatment or the technique on the mediator on outcome. So it's usually calculated by taking the estimate for A here times the estimate for B, so A times B, while adjusting for this direct effect here. This is very, very kind of simplified diagram, but this is the simplest form of mediation analysis, so to speak. And it has some weaknesses, because even if this independent variable here is a randomized treatment variable, if it is, we can draw say that and everything is done, according to state-of-the-art experimental research, we still can only draw inferences of causal inferences for the direct effect, the C path here, and the effect of the treatment on the mediator, those that involve treatment directly, but we cannot still draw any causal inferences for the B path here, the mediator's effect on outcome, because the mediator is almost by definition not randomized, because it's affected by treatment. So it's and that could be other causes of a relationship here between the mediator and the outcome. And then we also have the problem of when to measure the mediator, because if we only measure the mediator before and after therapy, we have no way really of determining the causal direction between the mediator and an outcome. We only know that they kind of change in the same at the same time, more or less. So some have suggested that we need to measure the mediator during treatment as well. Otherwise, we'll not have like a temporal precedence because we need to establish that the cause comes before the effect. And we cannot do that if we only have like pre-post measurement. So some have suggested that we need to measure the mediator during treatment as well, but is this really enough? Because then we need to find the exact spot where the mediator has changed, but outcome has still not really occurred or changed. The outcome variable has not changed yet. And how do we know this time point when we believe that the mediator will change first and then outcome will change after that? But how do we find the right time for that? And to make it even more complicated, this could be at different time points for different individuals. So that makes it really difficult to know and to establish this temporal precedence in this kind of design. Therefore, I come to believe we should do it this way, and don't be too scared of this picture because it's a bit complex, but because this is more like I will show you this picture again at the end of this talk, and by then hopefully things will be a bit clearer. But I wanted to show you this because this is what we're kind of aiming for here. So we have here the treatment. It's the same as in the previous picture. And here we have repeated measures of the mediator and of the outcome. So the M stands for mediator and Y is for outcome. It's usually or dependent variable. That's kind of a traditional way of putting it. And if you look at the green arrows, we see that the treatment has an effect on the mediator. All these green arrows with an A on. We believe that the treatment will affect the mechanism, you can say. Treatment will have an effect on the mechanism at every repeated measure. We can think of the 1, 2, 3, 4 as the sessions of therapy or the weeks of therapy. So we measure the mediator every week of therapy. And we also measure outcome at every week of therapy. So week 1, week 2, week 3, week 4, and so on. So we believe that treatment will have an effect on maybe not on session 1. Maybe session 1 is kind of an assessment of something. But the idea is this, that the treatment will have an effect on the mediator in every session, and the mediator in turn will have an effect on outcome, but maybe on the next session and the following session. So we first change the mediator, then the outcome. So that's the B paths here. They are equivalent to the B path here. So the A path is equivalent to the A path here, and the B path is equivalent to the B path in the previous slide. But we have several A paths and B paths here. And we also have these C paths that are the direct effect is also the same as in the previous picture. That's the direct effect of the treatment on outcome that is not explained by the mediator. So here we would believe that the treatment is causing change in the mechanism, which in turn will cause a later effect on outcome, but we don't have to. We believe that this happens all the way throughout treatment. It doesn't happen at a specific point, which can be determined on beforehand, but it happens continuously throughout treatment. And we keep the time precedence here by having the mediator affecting outcome in a lagged, time-lagged version. So it's mediator in time 1 affects outcome variable at time 2. So outcome could be like depressive symptoms or anxiety symptoms or something, functioning or whatever. Okay, so then we would be able to get an effect of the indirect effects of treatment on outcome via the mediator at all time points at the same time. Okay, so this is kind of a messy image. It's might not be completely clear yet, but I will go through all the basics after this to enable you to understand how this works, because we have all these other arrows here. We have these arrows, for instance. What do they do here? And we could also have other arrows like from here to here and so on. And to guide you through this, I will use an example from a published psychotherapy research paper. And it's an example from cognitive therapy. So it's outpatients with major depressive disorder who are treated with a classic cognitive therapy. The outcome measure is the BDI, the Brecht Depression Inventory, so the depression severity measured every session. And the mechanism, or the postulated mechanism, the candidate mechanism is change in cognitions. It's called, there's a scale for measuring, I think it's a self-report measure asking patients if they have experienced a change in how they think about their themselves during this session. So I will use the estimates from this published research paper just to illustrate the methods. It's not about that study, or we're not interested so much in the exact findings there. I just use it to avoid this having X and Y and stuff, because it gets kind of abstract if we do that. So we have these various elements of this cross-lagged panel model that I showed you before. And we have one of these elements is the so-called autoregression. So if I just go back to this image, we have this here. We have these horizontal arrows, and we also have them here in the mediator. And this is often interpreted as inertia, something that is kind of stability. It's not exactly the same thing as stability. Persistence, sometimes called, or carryover, something that is carried over from the previous measurement of the same variable. So here we have the BDI, which is the depressive symptom severity, measured at session 1, 2, 3, 4, and so on. And we do believe, of course, that depression at one time point will be not completely unrelated, in the same person, that is to say, will not be completely unrelated to depression when measured 1 week later for the same person. So it's likely that there's something that will be common. It's not going to be random how people fluctuate in depressive symptoms from 1 week to the next. So this arrow here is thought to capture, is used to capture this persistence in depressive symptoms. And in this case, this alpha is sometimes used by the Greek letter alpha. It was estimated to 0.66, and this is the autoregressive coefficient is it can theoretically be any number, but it's very often, or usually, I've never actually seen it go beyond 1. So it's usually like a correlation coefficient going from -1 to 1, although usually it's positive. So usually it's from 0 to 1. And I won't go into what it would mean if it would be higher than 1. It is possible, but it's very unlikely in psychotherapy research. So what this means here, and actually I think I should go to the next slide here. What this path diagram means, it's actually just a way of depicting mathematical equations. So this is like if we just take BDI2 and BDI1, it's like a linear regression model here. So we have BDI2 is explained by BDI1 times 0.66 plus this error term, or residual term, we could say here. So that's actually, it's just a common regression model. It's just that here it's this like several regression models chained together. So we have also BDI3 is explained by BDI2 times 0.66 plus epsilon 3. And we can capture this by this compact equation saying BDIT, so T is the 1, 2, 3, 4, etc., is equal to alpha, this one, the autoregression coefficient, times BDI at T minus 1. So if we have BDI2 here, BDI T minus 1 will be BDI1 plus epsilon T, which is this one. So that's what this means, this diagram. And we can also put it as time-specific equation, saying, as I did before, the BDI2 equals alpha times BDI1 plus epsilon 2, and so on. And the fact that these are the same values for all here is just that these are usually estimated as one. It's just one coefficient. So it's they could, in some models, we can allow them to be different, but in many models we just constrain them to be equal over time. And not going into that much more in this talk, actually. So most of the coefficient will be equal over time here, and there are sometimes ways to testing whether that's a realistic assumption. If we just stay with this very simple autoregressive model, we can also see that there are actually indirect effects already in this very simple model. So, and this is not like it's not the kind of like a mediation model, like the one I talked about previously, but mathematically it's the same thing more or less. So BDI1 will also have an effect on BDI4 via all these others measurements indirectly. So we can see that by just following these arrows, that BDI1 causes BDI2, which in turn causes BDI3, which in turn causes BDI4. And I say causes because that's the kind of underlying assumption. That's something we believe, but there might, of course, be other causes for these coefficients, since this is observational data. Yes, so and the indirect effects here, we can actually see them also in these mathematical equations just by inserting the equations into each other. So the indirect effect of BDI1 on BDI3, we can just use the equation for BDI3, this one, the green one here. It's alpha times BDI2 plus epsilon 3, as I said before. But we take BDI2, the equation for BDI2, which is the red one here, and we insert it inside here. And then we get this equation here. And then we see that BDI3 is explained by alpha times BDI1 plus epsilon 2 plus epsilon 3. And this means actually that the effect of BDI1 on BDI3 will be alpha times BDI1. So it's alpha squared. And that's, we can see, this is the same thing as we saw in the, as I said, in the mediation model. The indirect effect is, as long as the variables are on the same scale, it's actually the two component effects times each other. So in this time, this is 0.66 times 0.66 here. And we can do the same for BDI2, obviously, on BDI4, or BDI1 to BDI4. So we see here that it's also already becoming quite complex already in this fairly simple model. And we can see also that the indirect effects will decrease with the longer the lags there are. So the lag 1 effect here is that's 0.66. We already know that. The lag 2 effect will be this one times this one, which is 0.44. And the lag 3 effect is BDY1 on BDI3. That's alpha, how do you say that? Cubic version of alpha, 0.29 anyway. So the further apart the measures are, the smaller the indirect effect will be, as long as these effects are below 1, which they usually are. And then we can add other things to this to make it a bit more interesting, not just following depressive symptoms over time, but here we have the predictor, the CC, the cognitive change variable. And I've made this a very simple diagram here. So we have the same thing here, the BDI, the autoregression process up here, which is actually the exact same one in the process as previous pictures. And then I just added the CC at the same time points, and with this lagged effect. It's called the cross-lagged effect because it crosses from one variable to the other, and it's lagged because it's one time point before the other one, so to speak. And here we have the estimate. The beta is minus 0.11. So the more someone experienced cognitive change in a session, the lower depressive symptoms will be in the next session after adjusting for the autoregression effect, which is the stability in depressive symptoms from the previous session. And here we can also see another important thing about the autoregression coefficient, because if we didn't include this, then we would assume that everyone are the same at this time point in depressive symptoms, and they most likely are not. So we want to adjust for their previous level of depression here when estimating the effect of the variable that we're interested in. So including this makes it more like we are estimating the effect of change in depressive symptoms from the previous, because we have taken this inertia or stability, or what we want to call it, in depressive symptoms into account already. So what we have after that could be called residualized change. Sometimes it's when we adjust statistically for the previous measurement. And again, we see I've constrained this. We have constrained this to be equal over time. So we estimate it as if we assume that it is equal over time, and we have this same estimate for every cross-lag effect. It's possible to include higher order lags. That would mean that we would add another arrow here from CC1 to BDI3 and CC2 to BDI4 and so on. We would add that. We wouldn't skip this one, because if we skip this one, we would assume that the effect was delayed and there was no effect, immediate effect, and that would be, it's usually not what we would, I mean, it usually makes most sense that we would have an effect that is at the smallest time difference, so to speak. And then we would see if there's additional delayed effects here. Anyway, I won't speak too much about this because this is the kind of introduction. Yeah, and here we also see something interesting about this. If we take this together with what I talked about previously about the indirect effects in the autoregression here, that if we follow the arrows again, we see that CC1, it has an effect, a direct effect on BDI2, but due to this autoregression, it will also have an indirect effect, even if we don't include this direct arrow from CC1 to BDI3. It will still have an effect on BDI3 that goes indirectly via this BDI2. So this effect actually kind of travels forward in time, so to speak, because because we have this autoregression effect. And in the same way that I talked about before, the effect will be smaller and smaller with time, depending on the size of this autoregression effect. And this, to me at least, this makes quite a lot of sense, because if we make a change in something, we work with the patient's cognitions. We believe that will have an effect on the patient's depression level, but we don't. But we don't believe that effect to disappear immediately at session 3. Then it wouldn't be maybe the best intervention, because we believe that we will linger on. The effect will linger on over time, and then of course we continue working with this in the next session, and then we hope that this effect, that it kind of accumulates over time. And then it's also possible to calculate what we call long run effects, and that is what would happen if we got a stable increase in the predictor, the cognitions here. If we could have like raise the or reduce maybe the distortion of cognitions over several sessions or weeks, then what would be the expected effects on the patient's depressive symptoms? And there's a formula for that, but it means actually that we kind of raise this variable one step, and then it keeps on being higher, one step higher throughout the rest of the period here. Then we would expect the effect to be beta divided by 1 minus alpha, which means that the higher alpha is, the smaller this denominator will be, and the higher the result will be. And obviously also the higher beta is, the larger it would be, but that's not very surprising. So in this case, I just used the minus 11 here, the beta estimate, and the alpha estimate here, 1 minus 0.66, and it turns out to be minus 0.32. So even if it looks like this minus 0.11 looks like a small effect, it turns out that if we actually were able to increase CC more stably over time, then we would get an effect that would be at least moderately sized, larger at least in this sense. So because I mentioned this because we all often see what looks like very small effects in these kinds of studies, but they may not be, because we usually study the effect of changes in one variable on changes in another variable, with usually like just 1 or 2 or a few weeks apart in time. So it's not really like comparing pre-post effect sizes and stuff like that. This is something different, but this long run effect may be more comparable to these long run effects. To these pre-post effects. And then I also want to mention a few other things that we can do with these cross-like panel models, because it makes sense to think that if we have an effect of cognitions on depressions, there may also be an effect of depression on cognitions. So we may want to include that possibility in our model, and it turns out we've done some simulations of this, that if we don't, we may get very wrong estimates for this. We're usually mostly interested in this beta estimate, but even if we are only interested in this one, we may want to keep this, or may want to estimate this. I call it gamma here, the reverse causal effect, so to speak, because otherwise we may get the wrong estimate. We might. Because we're assuming something that is not true in the data. And here it turned out, and I think this is coincidence, that this gamma estimate was exactly the same as the beta estimate. But that it's not constrained to be equal. It's not that we're assuming that these two are equal. They just turned out to be the same size in this particular study. And but we have constrained them to be equal over time. So the gamma here is the same as the gamma here. The gamma here, that's the kind of a part of the model assumptions. But the interpretations is the same as this one, although opposite. So it's the effect of a change in depressive symptoms at this time point on cognitive change at this time point. And then we can also add the possibility of autoregression in this variable. And it's the same here. It turns out that this is important to include this possibility, because if we assume that there is no autoregression here, we might get the wrong estimates for the other parameters in the model. And here it turned out that this was smaller than for depression, but it was still there was still some. Yeah, I'm pretty sure it was statistically significant at least. And the interpretation here is the same as for here. It's like this inertia or stability over time that we're estimating here. And it makes sense to think that if we think that depression will have some inertia, then cognitions will also have that. And this is like the classic cross-lag panel model. We have actually one more thing. Yeah, right here. To get to the classic cross-lag panel model, we also want these error terms to be allowed to be correlated at the same time points. Because otherwise we are forcing things to all the relationships between the variables to go through these cross-lag paths, and there may be other things in these variables that make them related, and therefore it makes sense to add these covariances among the measures at the same time point. So this is actually the classic cross-lag panel model. Yeah, right, it is. But let's see what the time is. I'm a bit slower than I thought. I have one more issue that I want to mention about this, and that is that since people started to work with multi-level models, we have become sensitive to the fact that people are different. And here we have a data set. It's not the same data set actually that I talked about previously, but it's also with the BDI. And it's a depression measure over time. So it's similar in that sense. And it's for many individuals. All these lines are for different patients. And as you see, it's a complete mess. Some of them are starting very high and they are keeping very high, and others are starting low and they are staying low, or sometimes even they get worse, and so on and so on. So we have all these differences over time, but we also have the differences among people. And I kind of simplify that by saying we have this within person or time series part here, which is the repeated measurements over time. And we also have the between person or the cross-sectional part, that people are different in various ways. And if we just take this data and we put it into this kind of model, we will mix up these two dimensions. So we won't be sure that whether these things are actually stability coefficients within persons, or if it's like the relative standing of people relative to each other that it's representing. So it becomes hard to interpret. So therefore we want to separate these two parts, because for this kind of model we are mostly interested in these changes or fluctuations over time within persons. But we still want to, I mean, we could do this like one person at a time, but it's very hard to do that with only a few time points. If you have very, very long time series, again, you can use time series analysis and do it one person at a time. But in this case, we want to put them all together into the same analysis, because then we can do this even with fewer time points. One way of doing this is by centering. And I've just put in this graph to illustrate what this means. We center them on their own mean, which means that we essentially are taking out these between person differences here. So if we take this person up here and we take all these scores minus the average of all those scores, we will get this. You see the shape is exactly the same, but we have a mean of 0 for that person. And we do the same thing for all of these graphs. And for this one is this one. So it's the same shape, but we have taken out the mean and so on. So they will all have the same mean, which is 0. But we keep the fluctuations over time. That's the easiest way to illustrate, but unfortunately we cannot do that and just, we cannot use this manual centering and just put it into a cross-like panel model, because there's a problem with that. And I don't think I have time to get into that, but you just have to trust me for the moment here. I could if I had more time, I could explain this a little bit better, but it's actually a problem when we take do this observed mean centering. So we have to do it in another way. And I just skip this and go to this model. This is called the random intercept cross-lag panel model. So this is like taking multi-level modeling and combining it with structural equation modeling. So this, if you look at these circles in the middle here, that is the cross-lag panel model. But we have separated that from the means, which are captured up here and down here with latent variables. So this is like the centering, but it's done using latent variables. And that way we will avoid this problem that I just skipped and just mentioned. And then the cross-lag panel model is estimated among these latent deviation variables. There are other models, I should say, that accomplishes this, and they have all their kind of pros and cons. But that's for a more advanced course. If I just go back now to this image again, the mediation model, I just wanted to mention that we can see here, if we do this, if we take the cross-like panel model and combine it with mediation model, we get something like this. And I've skipped some of the extra things that we can do with the cross-like panel model, like the reverse effects from the outcome to the predictor or the mediator in this case. We could include that. But even so, we could easily do that. And we could estimate this model with using a cross-like panel model, and we could get all these indirect effects on final outcome. And if we had more time, I would have given you the assignment of counting the number of indirect effects here. So it would be, I mean, if this was assumed to be the final session, if it's just 4 sessions, then we would have like one indirect effect going up here all the way, one going up here and all the way, and we would also have like one here, so like this, and so on. So it's quite kind of many. And if we also had these reverse effects here, we would get even more. So this is why it's called a dynamic model. You can see that a change in one part of the system will get accumulating effects in other part of the system. And this is partly why I like these models, because they reflect the kind of complexity that I believe is actually there in reality. So to just sum up this, because I think my time is out, the idea here is to use cross-slide panel models to test the causal direction in longitudinal observational data. And if we also combine this with the separation of this between and within levels, we also adjust for some potential confounders that are stable over time. They will be in this these latent between variables rather than in the within level. Everything is not solved by this. There are challenges. We have this about finding the right lag structure, which may be a problem. Is it like realistic to think that there will be an effect from 1 week to the next, or should it be 1 month, or should it be like even shorter? And how do we measure that if it's things are happening in a very rapid time scale? To get to kind of a full causal analysis, we would need some way of adjusting also for time varying confounding, which is possible here. We could have other variables changing over time at the same kind of or related to these variables, changing in the same kinds of ways that are the true causes, and we're just observing something that is not the true causes. There are some newly developed methods that might be able to do this in the future, but currently they are hard to use on these kinds of data. And I've included some literature suggestions, and I think we can email out these slides, hopefully, to people so they can don't have to write down these literature suggestions. These are some of the most important ones, I think. And I've also included some of the ones that I've been involved in myself here. And something strange here. Anyway, and is also some code here that you can use. You can use these links to get codes for R and M+, I think. Yeah. So I think I should stop there, actually. I'm sorry if this got a bit stressed up at the end here, but I hope it was possible to follow to some extent, at least.
Thank you so much, Fredrik. Very clear presentation on such a complex topic. We have some time for questions. Can you stop sharing the slides so we can? Thank you. So is there any question? I can start with one. My question is, what are the constraints in terms of sample size for these kind of models? Can you work
with sample size? Yeah. It's a good question. It depends on a few things. It depends on the complexity of the model. The more complexity, usually the larger sample size you need. And particularly, it seems to depend on whether we can constrain these coefficients to be the same over time. Because if we can, we also kind of we can do it with smaller sample sizes, because we also have these repeated observations that's kind of another dimension of sample size, so to speak. So it's we get more observation. If we had like 10 repeated observations and 50 people, that's like 500 observations, which in a sense, although it's they are good for different things. So if we can constrain the coefficients, if that's realistic, then we gain stability for the model due to that. So I wouldn't say anything, but I think maybe like 50 would be really the absolute limit for the smallest sample size. And usually we would need like 100 or maybe even 200 or something. But it all depends on various things, and I wouldn't really say something that's for everything, works for everything. Sorry for that, but it's not really possible. And I have there's a question from Jacques Barber. Thank you, Fredrik. How do you handle multiple mediators mechanisms? Well, that's a good question as well. If we have, in principle, you can put in multiple mechanisms or mediators in the same model, but it becomes a huge problem if we have many repeated observations and we also have several variables. I would say it quickly becomes intractable, because these models are estimated from the covariance matrix, including all these. So every repeated observation is one variable. So if we have like 10 repeated measures for every variable, then we have like a 10 times like 4 or 5 or 6 covariance matrix, and this becomes huge and becomes really hard to do it. And also it becomes hard for the software to do it unless we have like a huge sample size to calculate it from. And it also becomes difficult for us to specify the code, because there are so many things happening that we need to take care of. But in principle, it's possible to use it with like 3 or 4 variables at least. I've tried it with 3 variables and it's worked quite well, but you have to be careful, and usually we have to build it up with like 2 variables first and see how that works, and when you can add a third one to see what happens. And we have to go back and see if we have made errors along the way and so on. So in principle, it's possible to do it with several variables, but it's difficult. That would be my response.
The reason I'm asking is because I'm interested to compare different mechanisms and to know which one is really the potent mechanism. So how do you suggest doing that with the samples we have?
Yeah, that's right. What you can do, if we have enough, if you have many repeated measures, like 10, 15, 20, or even more, then you can do it in long format. And there's this framework called DSEM, Dynamic Structural Equation Modeling, which can do cross-lagged panel models on long format data, and then it's much easier to get it. Then you can have easier have more variables. But it's a difficult when you have few measurements and we have also very complex models. That's
okay. Thank you. Thank you very much.
Thank you. There is another question here in the panel. Is it possible to conduct a single case study?
Yes, although that's another there's another kind of estimation. Then it's a time series analysis that you use, and then you usually need many more repeated measures. So instead of having a large sample, then you have a large sample of repeated measures, so to speak, on the same individual. And I don't know that literature that well, but I think like 20, 30 or something, or I think even more, maybe like 50 or 100 repeated measures you usually need to be able to do that. But I don't know that literature too well. But the models are can be quite similar. You can do this like cross-lag model for time series and data as well. Then we have Pauline.
Yes, thank you. Thank you for the talk. I think I got what it is, what it does, and why.
Great, great.
I have a question about the best current computing environment for that. So can you calculate this with an R package, or what is the best way to go here?
Yes, we have this package called Lavan, Lavan, which is good. I haven't seen any comparisons. I've used M+ a lot, and I've used R a little bit. I think M+ has some more features still, and it's probably probably a bit more stable as well. But I think Lavaan is good, and there are other packages that I don't know of, but I'm sure there are other as well.
Great, thank you.
And at least one of these links that I provided is for the code for Lavaan. Yeah, there it is. It's on this. Oh no, sure you don't. I don't share my screen anymore. But if we can send out these slides, then there will be these links that you can follow for.
Great, thank you.
Code.
Fredrik, can I ask, the model assumes continuous stability, doesn't it, with the autoregression? So does the model assume a continuous stability of improving measurement over time within the model?
Not really, actually, because it's estimated from the data. So if there is no stability at all, then the autoregression coefficient will be 0. Or even if it's really chaotic, it could be negative. So if the one variable is high at one moment, it could be low at the next one, and we would go like this. So it doesn't really assume that.
Your BDI measurements were, of course, sinusoidal, which outcome measures tend to be, and that can be confounding, can't it, for the cross-lag panels? Is that right?
Then you get into one of the topics that I didn't have time to get into this, because I think, at least if I understand your question right, it's about the possibility of trends in the data.
Yeah.
And we actually have just, I got a response from a journal right this morning from a paper where we've written about that.
Right, okay.
Basically I would say you're right. If there are trends that are kind of coming from other sources than the autoregressions or the cross-lagged effects, then those can be confounded and they could be a problem. But you can't really see that from just observing the data, because some trends could result from the cross-lagged effects as well. So.
But there are ways of working around that. And the complementary of that is that, of course, mechanisms of change aren't continuous either. I think that cognitive therapy paper assumed that every session had mechanisms of change within it, whereas actually when you do observational studies of videos of the mechanisms of change, actually there might be an event which you're looking at for a mechanism of change, which is in session 3 and in session 7 and session 8. And actually, does that make a difference, Freddie? I mean, is it?
Well, if it's really like discontinuous, like it's something that just happens in very few sessions, then it would be hard for these kinds of models, because these are linear models. They assume continuous variables. You might be able to see it while looking at the distributions of the data and find some other kind of it's possible to do these models using assuming other distributions of the data, but that would be really much more advanced stuff.
Okay.
And
okay, I was hoping you'd give me a simple answer for that one.
Not really. Not if it's. I mean, if it's more happening in some sessions than in other sessions, then it would still be kind of continuous, and it would probably be possible to still use this. But if it's really like happens only now and then, and it might also be different for different.
This is going to be likely in a lot of therapies, though, isn't it? But particularly psychodynamically or exploratory therapies, the change events are likely to be less regular and continuous.
Might be.
Right. Okay.
It's a good question. You might be able to kind of rescale it also into some kind of a 0-1 variable, or use some.
Could you,
like
if you
that.
were doing, sorry, I'm hogging this, but if you were, I've got you now, Freddie. If you were, could you isolate the sessions in which the change events that you were looking for were happening and excluded the sessions where there wasn't a change event that you were looking for? What would happen then? What would that do to the model?
I don't think you would be able to do that.
Okay.
But I mean, what I think still, I mean, even if it's like more happening in some session than in others, or in some session nothing happens, then it wouldn't really be a problem, because we would still be kind of continuous. It's kind of if it's really like nothing happens in 10 sessions out of 12, and in 2 of the sessions there's lots of things happening, and you would need to have some other kind of then it would be violating the distribution assumptions of this model, and we would do. But it would still be possible for the model itself, but you would need to have some other kind of logistic regression or something in the model, or like count data. They have these distributions that looks like this. So something like that you would probably need to do.
Okay. All right. Thanks, Freddie. Yeah.
Thanks.
Thank you very much for this presentation, Fredrik, and for all your questions. Next week at the same time, we have another webinar by Irene Messina, titled Understanding the Mechanisms of Psychotherapy Action, Insights from Effective Neurosciences. I hope that in the next few days, you will receive in the listserv the link to register. So if you want to appear, please do that, and I'll see you next week. Thank you once again. See you soon. Bye-bye.
Bye-bye. Thank you.
Thank you.